This video lecture is going to emphasize one of the last early gas law relationships that has a name, as well as just reviewing again and emphasizing how I want you to set up these problems before moving into the ideal gas law, which is going to showcase all of the variables combined. So we've looked at Boyle's law, Charles' law, Gay-Lussac's law, and all of those look at pressure, volume, temperature relationships, isolating two of those variables. And there's an unnamed one that a lot of you have connected, which is pressure and an amount. So moles, number of particles, and it does not have like a name to it, but it looks similar to Avogadro's law, which does have a name, and that is volume and amount. And so if you have pressure and amount, you can imagine that if you increase the number of gas particles and you keep the volume the same and the temperature the same, then the amount will increase. Well, that works if you have a fixed container. You'll see that relationship there, and it doesn't have a name. But Avogadro's law is where you have a flexible container, like a balloon. So I think of this relationship like blowing up a balloon. If you add more particles and you keep the temperature the same, you have a flexible container, then the amount of space the gas particles will take up will increase. And you guys have kind of already learned Avogadro's law at a very specific set of conditions, which is STP. So at standard temperature and pressure, so at 0 degrees Celsius and at 1 atmosphere pressure, or 273 Kelvin, okay, 1 mole of any gas at STP will occupy 22.4 liters worth of space. Now you don't have to have 1 mole of gas, and you don't have to be at standard temperature and pressure. And so you can then, if you know how many particles you have, you know the temperature and pressure, you can solve for the volume. That'll be what we will cover here next. But if you just want to look at how the volume will change based on the amount, keeping temperature and pressure the same, whatever those conditions are, you could then measure that with Avogadro's law. Okay, so this law can apply at any temperature and pressure as long as that's constant. It does not have to be at STP, and you can literally change the amount of particles and then predict how much space they will take up, assuming you have measured the temperature and pressure. So you have to have a flexible container to look at Avogadro's law. And just like if you were to want to look at the amount of particles and how pressure changes, and you'd have to have a fixed container. So something that is inflexible. If you add more, then you could measure how much pressure it would be. They are direct relationships. This should, this kind of relationship with the proportion there should look like Charles and Gay-Lussac's law, because as one variable goes up, the other goes up. And amount needs to be in moles in order to compare the two volumes. Changes there. So that's just Avogadro's law there. And so that's kind of like a lot of the combinations that you can have with just isolating 2 of the 4 variables and the ones that have names. Now you've been introduced to all of those. The practice problems, again, for any kind of graded problem, to remind you, what I need to see is I do need to see the equation used. So you have to identify what equation you're using or what variables are being measured and how they are related to each other. So usually it's either Boyle's, Gay-Lussac's, Charles' law. The combined, if you're using pressure, volume, and temperature, Avogadro's is there. If it was pressure and amount, then you should be able to put those written like Avogadro's law, but just with pressure and amount. I do need to see the variable that you're solving for isolated before you put any numbers into the equation. So because I do want to see unit cancellation in an answer with sig figs and units. A lot of students don't like to do this. They like to put the numbers and then just leave the variable that they're solving for on one side of the equation, and then they just give me the answer, and they're not really showing me the skill of dimensional analysis and rearranging an equation algebraically. So just to emphasize again what I'm looking for with a problem like this. So it wants to know, what will the final pressure of a gas sample be if it's initially at 2 atmospheres and it's changed from 42 liters to 124. I get something like this is a pretty simplistic problem, but I want to emphasize the skills, not just the answer of the problem. The process is really important in showing your work. So it just mentions pressure and volume. So you could just write, P1 times V1 equals P2 times V2. And that would be the relationship between the two variables. You might not at first recognize how to set it up, or another way to do this is to write the whole combined gas law. So if you wrote pressure 1 times volume 1 equals pressure 2 times volume 2, that's perfect. One way to start, if it's only mentioning pressure, temperature, volume, is just write out the whole combined gas law. And sometimes students do this if they're not sure, just to see like, well, what variables do they have? It does mention atmospheres with this pressure, liters, and liters, which is measuring volume. Since it doesn't mention temperature at all, right, that means that it's remaining the same. It's assumed to remain the same, so you'd cancel it from both sides, meaning it would be the same number. We are looking for final pressure. It doesn't matter if we pick P1 or P2 to be the final pressure. It's more important that we match the numbers. So it says it's initially at pressure of 2 atmospheres, and then it goes from 42 to 124. So the 42 liters is our initial volume, like it's linked with the 2 atmospheres. So you could make those both the 2s. I like to make whatever is initially the 1s and what's the 2s. So we are solving for pressure 2 based on how I've done it. And so to rearrange this, I need to, divide both sides by V2, or sorry, by V2, or multiply by the reciprocal of it. And so pressure 2 would be equal to pressure 1 times volume 1 over volume 2. So I want to see the equation rearranged for the variable that you're solving for, and then do a number setup. So for this, it's going to be pressure 2 is equal to pressure 1, 2.0 atmospheres, times volume 1, 42 liters, all over 124 liters there. And when you do the math here, you will get a pressure 2 with sig figs. You're only going to get 2 sig figs there. Put it on this other side. Your calculator said like 0.6774. You're only going to get 2, so 0.68 atmospheres would be the final answer with significant figures. And then you can always check, like, does this make sense? So volume is increasing. If the particles have more space and temperature and amount is staying the same, then they would hit the walls of their container less frequently. And so we would anticipate the pressure going down. And so yes, going from 2 to 0.68 seems reasonable. So this next problem wants to know, what is the volume of a gas if it's measured at 0.950 atmospheres and 25 degrees Celsius, if its initial volume is 26.3 liters, 1.25 atmospheres, and 14 degrees Celsius. So this problem mentions temperature, pressure, and volume. So I'm going to use all of the variables in the combined gas law. So I'm going to write that equation. I am solving for final volume, so that's going to be V2, and V2 rearranged to get it to be isolated. I'm going to multiply both sides by T2 and multiply by their reciprocal of pressure 2, or divide by pressure 2. Do that on both sides of the equation. And so volume 2 will then be equal to pressure 1 volume 2 will be equal to pressure 1 times volume 1 times temperature 2, all over pressure 2 times temperature 1. I do need to make sure that the units are in the correct units for these problems. So my pressure does match, and then this is pressure 2, this is temperature 2, volume 1, pressure 1, temperature 1. I do need those temperatures in Kelvin, because 14 degrees Celsius to 25 degrees Celsius makes it seem like the temperature is almost doubling, but it's not. If we put it in Kelvin, Kelvin scales it proportional to the kinetic energy. And so you add the 273, and for temperature 2, it's going to 298 Kelvin. And for temperature 1, it started at 287 Kelvin. So when you put it in Kelvin, you can see like 287 to 298 amount of kinetic energy is nowhere near doubling. And so Kelvin is the only temperature scale that sets temperature proportional. I do find that if students label the variables in the problem, they're less likely to make a mistake and put stuff in wrong, because at this point it's then just like plug and chug here. So pressure 1 is the 1.25 atmospheres. Volume 1 is the 26.3 liters. That little bit of lag here going on. And the temperature 1 is 287 Kelvin. That's all going to be over pressure 2, which is the 0.950 atmospheres, and the 298 Kelvin here. I'm going to just plug this in. Another thing that sometimes students do incorrectly is they have an order of operations error. So just be careful when you're typing this in, that everything on the top is multiplied and then everything on the bottom is multiplied before you then divide it. Or I type it in 1.25 times 26.3 times 287, and then I divide by the 0.950, hit enter, and then divide by 298, so that both of those are proportional there. And I get a volume of 33.3. And then we can check that the units cancel. And again, it's just a check. I'm just giving you like things to think through after you have done the plug and chug. So you have atmospheres that cancel, and Kelvin that cancel. The only unit that doesn't cancel is liters. Should make sense since you're solving for volume there. And then you can also kind of think through pressure went from 1.25 to 0.95, so it decreased. So we'd expect volume to go up, and then temperature went up. And so again, we would expect the volume to go up. The volume went from 26.3 to 33.3, so that seems reasonable. And sometimes if pressure and temperature like get contradicting, what would happen, then you have to kind of see like, well, which one goes up more or goes down more, to kind of see which variable might tug at the change in the volume more carefully there. So that's another one. I just want to do one last one, because sometimes students solve for, if you're solving for final temperature, incorrectly. And so if you feel good about this type of problem, see if you can solve it first, and then pause, and then see what you come up with. Otherwise, I'm going to talk through it, and I'll give the answer right near the end of the video. So this is pressure and temperature, and it wants to know what the new temperature is. It's standard pressure. So standard pressure is 101.3 kilopascals, or 1.00 atmospheres. It would be an infinite number of it's not going to limit our sig figs here when we are saying standard pressure. We do need to change that temperature into Kelvin. So add the 273, and you're going to get 323.0 Kelvin when you're adding it. Since the 273 is a constant, you want to keep the same level of precision as the temperature measurement there. And so you're going to get the 0.0. So you're going to have 4 from that, but your finalizer should only have 3 because of that pressure one. So we're looking at pressure and temperature. And as one goes, pressure is going up, so the temperature goes up, but by how much is what we have to solve for. For this, a couple different ways, to rearrange it. Just make sure you don't have a reciprocal answer. So I like to just cross multiply. And again, I want to see the variable rearranged. So pressure 1 times temperature 2 equals temperature 1 times pressure 2. And then to get temperature 2 by itself, I'm going to multiply by the reciprocal of the initial pressure on both sides. And then I will have the correct rewrite of the equation. So temperature 2 will be equal to temperature 1 times pressure 2 over the initial pressure. And there's multiple ways to get there, but make sure that algebraically you can get there, and then you can plug in your number. So our initial temperature is 323.0 Kelvin. Our final pressure is the 1.00 atmospheres, and it started at 0.370 atmospheres. Again, when you're thinking through this, we already kind of anticipated what should happen to the temperature. It should go up, okay? And it's really going up by a factor of like 3 almost, because from like 0.33 times 3 would be 1. And so we should see a large increase in the temperature, almost 3 times. And I get, with sig figs, 873 Kelvin there. And if you divide that number by 3, you get like 290, which is close to the starting temperature of 323. This isn't quite going up by 3, and so it's a little off, but again, I'm just giving you tools in your toolbox to think, like, does my answer seem reasonable? So the pressure almost tripled, and so we would expect, because it's proportional, the temperature to almost triple. And just make sure you don't get a reciprocal answer. So sometimes students will flip the pressures, and then you won't get the same thing, or they'll have they'll basically have 1 over temperature 2 is equal to whatever they have, because they did the algebra wrong. So just be careful on that, and make sure you know how to rearrange an equation when the variable that you're solving for is in the denominator starting off. So this video is just, again, giving you a little bit more on the early gas laws, and then next video is going to be into the ideal gas law and some considerations we have to think about with that.